All right, hey, this is Horner, and this is the 2011 AP Physics C Mechanics question number 1. This is a pretty, not a really bad equation or problem at all. This one's pretty easy. So we have a projectile that's fired from a launching device. There's a bunch of things that are going to go on, and the first thing they want us to do is find the time required for the projectile to travel through the length of the launching device. Then they're going to have us find the mass of that launching device. Then they're going to fire it into a block of wood that is clamped to a tabletop so it can't move, and then the projectile travels a distance into the block before it stops, and they want us to find an equation or an expression for the work done in stopping the projectile, and then an expression for the average force on the projectile. Now they have the projectile and the block again, but the block is not clamped. The projectile is fired again, and it travels a new distance. And there's all kinds of friction here, so a really good problem, but a pretty lengthy problem. So one of the things that I did, since we're not going to get everything over here, is I've got a blank page. You'll want to do the same thing. You want to put all your answers on the blank page and then attach it to your original problem. That should really help you as you go through. So I'm going to open up the commenter here so that I can use all of the tools that we need. And here we go. So the very first thing they want us to do is determine the expression for the time required for the projectile to travel the length of the launching device. Pretty easy to do here. We know that if it's traveling through, there is a force and it is applied over a period of time. So the best thing to do is think about impulse, probably the easiest thing to do. So this is a letter A. This is only worth 2 points. Essentially, you can just say J, which is impulse, is equal to the integral of force dt. And so we also know that that is equal to, for the projectile, it could be equal to the average force. So as long as you put average force, you can do this. Remember, this is more specific than this is, but if we do the average force times the change in time. So big difference between dt and delta t. If you put the integral sign, put f delta t, you won't get it right, so you have to be really careful. So here we're just saying that we're going to use the average force times the change in time, and so our change in time then is just equal to the impulse or change in momentum of the projectile over the average force that is acting on that thing. There's a longer way to go through and do this. I would do it the shorter way. It just makes it a lot easier, and this way also makes a little bit more sense. For letter B, next thing we want us to do is find the mass of the object. So we know the impulse is equal to the change in momentum, which is, here we go, there it is, mass times the change in velocity. So our velocity we know starts at 0 and then goes to some speed. So this is the impulse of the projectile is equal to mass. And then we have the final velocity. So that would be the final velocity in the x direction minus 0. So this is just equal to mass times that velocity. So our correct answer here is mass is equal to the momentum of the projectile divided by that velocity, which is Vx. For letter C, here they want us to find an expression for the work done in stopping the projectile, so that is letter C. For letter C, this is another pretty easy one to do. We know that work is equal to the change in kinetic energy, and it did definitely change kinetic energy, so that is equal to final kinetic energy, which is 0, minus our original kinetic energy, which is 1/2 mv x squared. So the x here just tells it's over that position change, or how long the tube is. We can now plug in some of the things that we've done up here in order to get this to work out a little bit better. So work is equal to -1/2. We said that the mass was equal to Jp over Vx, so that is the impulse of the projectile over the velocity. And we've got to take that times Vx squared. We see that we can cross off one of the V's here and one of the V's there. So this is now equal to 1/2 of JP, and then we multiply that times, so I'm going to make this J a little bit bigger, there we go, JP times Vx. And that would be the amount of work that is done. Really important that you show that it is negative, and it is negative because there is work done on the projectile that is making it slow down. So if you didn't have that, that would be a problem. For the next part, they want you to derive an expression for the force, FB, exerted on the projectile as it comes to rest in the block. So that is the force of the block on the projectile itself. So this one's a little bit more involved. It's not really too bad. There's just a little bit more to it than what we just did. Oops, I went too far, so I'm going to scroll this back up again and then scroll it back down just to, oops, there I did it again. So I'm going to scroll it down just, okay, one more time. There we go. So now we've got letter D, and in letter D, we know that work is equal to the integral of force times dr, which is really just the average force times the change of position or the radius there. So now we can say that work is just equal to force from the block over that distance, and so our force from the block should be equal to the work over the distance. And now we need to plug everything in that we had. So we're going to plug in what we had for work. Remember, work here was equal to 1/2 of, oops, yeah, 1/2 of the JP times Vx. So this is going to be equal to JP, and this is force done by the block, so it's going to be positive. So that is JP times Vx, and then that is divided by 2 times D. Now, if you have the negative sign, that's also fine too, because that is the work done on the projectile by the block. So plus, minus, this one, it really will not matter. For the next part, they want us to now derive an expression, dn, for the, well, dn, which they define as that new distance into the block in terms of the original distance, the big D, ft, and fb. So here, this is that block sliding across, okay, the table. And that is big D, and then they give everything else in terms of what we've seen before. So we're going to get another blank page and do letter E and letter F. Alright, so here we go. This is letter E, and we know that the initial kinetic energy plus the work should be equal to the final kinetic energy, and there's work there, we remember. So here we've got the kinetic energy plus the work done by the block, and we also have work done by friction, and that is equal to 0. We're going to substitute in the work done by the block on the projectile, so we know that Ki plus the work done on the block was the Fb, so we're going to put negative, and it's important to have the negative here, even though we didn't need it in the other answer, Fb times the new distance that it travels, plus the work done by friction, and that is equal to 0. We know that the initial kinetic energy minus Fb dn, and then the work done by friction is negative force, force of friction from the table across that distance, d, big D, is equal to 0. The initial kinetic energy of the projectile is the same as the first case. The block was clamped. So we can equate this to the work done in stopping the projectile from part D is essentially what we can go through and do. So let's go ahead and substitute everything in. So here we're going to say this is F times B times D, so that was our original kinetic energy, minus FB, and then our new distance minus the force of friction from the table times D, and that's equal to 0. So now we've got FBdN is equal to FBD, so this is equal to F little b times little d minus the force of friction from the table times that distance d. So now all we've got to do is solve for dN, and dN is equal to FB times d minus the force of friction times big D all over FB. If you wanted to, you could go through and you could simplify this, or you can just leave it the way it is. I would just leave it the way that it is. Just kind of moving back up to what we had before. So there's our FB, and there's that work that we talked about in letter D. So that's for that mass when it comes into contact, or that dart when it goes into the block itself. And so that is letter E. For letter F, this one is the one with the momentum. And so now we can solve this with momentum. So what does the question say again? Remember, this one says drive an expression in terms of d, the mass of the projectile, and the mass of the block. So here we did it with this expression, and then we also found that new distance, and we're going to do it using d, the mass of the projectile, and the mass of the block. So for this first one we used one thing. For the second one we're going to have to use well, for the first one we use kinetic energy and work, or just change in energy. And for the next one we're actually going to need to use conservation of momentum. So we conserved energy and work here, and the next one we've got to conserve momentum. All right, so to do that in letter F, this is an extremely long problem. People really struggled trying to get it done this year, the year they gave this test. So that's 2011. We're going to start this one by saying mass times the velocity in the tube is equal to mass of the projectile plus the mass of the object that it hits times the final velocity. So our final velocity here is equal to m over big M plus little m, and then we're going to multiply that times Vx. The kinetic energy of that block projectile system immediately after the collision is equal to the work done by the friction stopping it, so that's 1/2 of the total mass, so that's m plus little m, which are the two objects, times v squared, is equal to the force of friction that we know is on the table times that distance that it goes. We're going to substitute in for v, so we're going to take this and put it in there. I know. So here we go, 1/2 of m plus little m. So this is big M plus little m times, and then this is little m. Do you see why we put that O on the little m's earlier, on the big M's earlier? So let's do that again. Otherwise this gets super confusing. Okay, so we've got little m over, and then we've got in parentheses big M plus m times Vx, and we have to square that, and that's equal to the force of friction from the table times that distance. Go through, do your math. You're going to end up with 1/2 of m squared Vx squared over, you've got m plus, so this is mo plus m, and that is equal to the force of friction times d. And then if we go through and simplify this, we can make it m over m plus, so this would be big M, so we're going to put that mo thing there, plus we've got m, and then we're going to take that times 1/2 of mvx squared. Well, there's kinetic energy for us. And then that is equal to ft So that force of friction from the table times that distance. All right, so now that we've done that, we remember that this energy is from part C, so from way long ago, is equal to the total work done. So this is equal to the total work, which means that I can now take M over, I don't know why I did that, but it did, capital M plus little m times FB, and then we said little d, and that's equal to the force of friction from the table times the distance. So the other thing we had is in part E, remember we had that FBD minus the force of friction, so that's this guy right here on top. So let's move this over so you can see it. So we said that actually it's this one, FB times D is this guy. So F that we want here, so we've got FBD is, yeah, there's our M over this. Okay, so there's that one. So now we're going to go ahead and say that that's equal to M over big MO plus M, so that's this part here, times that FBD. So there's FBD, it's little d, there we go, is equal to, and then we can, for this, plug in this expression, which is FBD again, minus F, force of friction from the table, to D. Now that we've done that, you'll see that the force FBD, so here's FBD here, here's FBD here. So remember, we're going to have to leave those D's because they're all very similar. So we've got all of this. Oops, you know what? This is the force M over MO plus M times FBD is equal to FBD minus, and then this really shouldn't be what I've got there, so let's erase it because we are substituting in for this FT. So that's FBD minus FBDN. So we can plug that in now. Minus FBDN. So this is FBD minus FBDN, so I'll get rid of that funky thing there. So you can see it, FBD minus FBDN. And so when you do that, you're going to end up with M over M plus M, so this is big M plus M, times D, because we got rid of the FBs all the way across. Bye-bye B, bye-bye-bye, and bye-bye B. We still have the D here. So that's times D is equal to D minus dN. And so when we're all done, we're going to solve for dN. So let's do that up here. And so this is going to be dN is equal to D times 1 minus M over big M plus little m. And that is your final answer. So lots of work here. All of this is 2 points. So it's just a crazy amount of work for you to go through and do. So if you get a problem and you start to do all this work, stop. At least you'll get the 1 point. Who cares about the other point? Just a crazy amount of work for this. So I'm hoping that you'll see that just as from this example. I want to add one more thing here while I'm at it, since I'm already at 19 minutes. Remember we were trying to substitute in here, and I was coming over here and using this. Notice that the FFTD is actually equal to FBD minus FB times FB times DN. And that's why I kind of made that little boo-boo that we did over here and had to erase. So you'll see kind of how that fits in now a little bit better, because this is equal to this guy minus this one. We had to take the negative all the way through and then add this to the other side. So hopefully that makes a little bit more sense.